Probably gonna tape it.
Wow. I'm gonna turn the light off this.
I guess he said that they're like second best player for a half. Wait, can't Luke said he's the best player, so we're second best player for the first.
Okay, we are going over a pre-calculus topic. You're going to enjoy this. The only thing today is a little bit wordy because we've got some theorems to talk about, but honestly, you don't have a lot of math to do tonight at all. No math. It's like find the max, find the min. Draw a picture that has a max here. Draw a bit. It's easy, so you'll be happy. Tomorrow will be fun. Funner.
Yeah. Good one.
All right, so do you remember what an absolute max is and an absolute min?
Yes.
What is the absolute max on a graph?
The top point.
No.
At the very.
It is the highest point on the graph, meaning you cannot go higher. The highest point on a graph. You cannot go higher. The absolute min then would be what? The lowest point. You cannot go lower than that point on the graph. I'm going to draw 5 pictures right here. I want you to copy them. We need to talk about them. Particularly one of them will be important for the next 2 theorems that I talk about. So, but I want you to have this idea of maxes and mins and what's happening, domains. It's a lot of pre-calculus stuff that we've done again. Let me do this one. We're going to do a good old... that one. And okay, there's those 3, and then I do want to draw, like I said, 2 more. One of these is important. Okay, sorry. There's a reason, there's methods to my madness. I need you to look at graphs and recognize and understand things. Okay, so a couple things here. One of these pictures is actually going to lead us into, like I said, what we're talking about in terms of the next, we're going to talk about 2 theorems today. And that's really it. It's not too much math. So let's talk about this first picture up here. This is your x cubed picture, just discount. What's the domain? All reals, right? Remember, domain would be, this is important that we talk about domain now, negative infinity to infinity, because we always have to go back to the domain of the function, okay? Is there a max or min in this picture, or an absolute max or absolute min?
No.
No, there is no, remember this goes off into infinity, so there is no max, no min. Second picture, what's the domain of this picture? Again, domain means how wide is this picture getting? All reals again. But does this one have a max or a min? It does. I probably should have put a little 1. I'll put a 1 here. Okay, so what would that point be called right there? Oops, sorry. That is your max. So there is an absolute max of 1 at x equal to what? 0. It's very important that you understand what I just wrote. The max is 1 when x is 0. That's going to come into play again for things we do. Don't be like, okay, yeah, duh, but please just make sure you know that. Is there a min in this graph? No, okay? There's no min. Good old cosine graph, for those who don't remember, cosine. What's the domain? How wide is this going if I kept going on and on and on? All reals again, domain. Negative infinity to infinity. Is there an absolute max? Yes. The absolute max is here, also here, also here. What is this value? 1. So there's an absolute max of 1 at x equal to, what's this x value? Do you remember what this x value is? Close, 2 pi. Also at negative 2 pi. So at 0, at plus or minus 2 pi, at plus or minus 4 pi, et cetera, because it's cyclical. It's off the unit circle. Is there a min in this picture? Yes, there is an absolute min of negative 1. The birds are chirping. At x equal to this, what's halfway between 0 and 2 pi? Pi. So at plus or minus pi, at plus or minus 3 pi, et cetera, et cetera, et cetera. Okay, so when we look at pictures that have domains of all reals, we could have a picture that has no max or min. We could have a picture that just has a max or just has a min. We could have a picture that has both, okay? Totally makes sense. We've done this before. Now we're going to talk about what happens when we have pictures on intervals. This is an interval, right? This is a closed interval of 1, 4. 1, 4. This portion to this portion. Does this graph right here on this interval have a max? What is the highest point of this graph on this interval? What is the highest point? 4. So it does have an absolute max of 4 when x equals 4. Does it have an absolute min? Where?
0.
No, absolute min of 0 at what? X equals 2. Good job. Okay, so here and here. Last one. Here's the picture, x over 2 minus x on the half-closed interval, open interval of 2. Does this have an absolute max? No. Why? Keeps going and going and going. Does it have an absolute min? Where at?
0.
Absolute min of 0 at x equals 0. So here's what we're going to talk about just to kind of give you an overall idea, which I don't think this is really, this one right here is probably the main one we're going to focus on at the end of today. Absolute maxes and mins can only occur at the endpoints on an interval or at this point right here, which is called a critical point. But then you're saying, but an absolute max occurred here. Look right here and right here and right here. What are all the slopes of those pictures?
0.
0. These are what's known as, we call them critical points. In mathematics, critical points have slopes of 0. And we want to find those critical points because we need to find absolute maxes and mins. That's the whole gist of this whole entire lesson today. If you learn nothing else, critical points are slopes, which are derivatives, which equals 0. And so we're going to talk about, and then maxes and mins can occur at the critical point or at a max or a min. So with that said, let me introduce you to our next lovely theorem, which is called the extreme value theorem. And I do like you to write all these definitions down because I don't want math to be scary to you. I think when you start reading definitions, they sound crazy, but they're not that scary if you break it down. So if f is a function and it's continuous over a closed interval, AB, then there is a point on AB for which f has an absolute max or min over AB. So extreme value theorem says that if you've got this continuous function, so there's no jumps, no gaps, anything like that, we don't want that, and you're on this closed interval, then there's got to be a point where you have an absolute max and an absolute min. And we saw this in this picture, did we not? Was I on a closed interval? Did I have an absolute max and an absolute min? Sure did. Was this closed though, entirely closed? No. If I had put a bracket here, then I would have had a max and a min. Does that make sense? Okay. So that's all this extreme value theorem says, that I've got myself some maxes and mins. Cool. How does that help us? Well, it leads us into the next thing. No, you're so excited today. Have you seen, well, let me draw this picture real quick. So you've seen this picture last year. Is this a max? Is this my maximum? My absolute max? No. Is this an absolute min? Is this an absolute max? Yes. Okay. However, these have slopes of 0. Agreed? This one, though, we've talked about this before, this is called a what? Cusp, and we can't take a derivative of it. So there's some other things that are happening here. If you remember, we don't just have absolute maxes and mins. We have what's called, last year we called them relative max and min. Do you remember that word? We're switching that word today in calculus to be called a local max and local min. And all that is, those are just the same as relative max and relative min. And what that means is a local max is a high point, but not the highest. So this guy right here, he's considered a high point, but he is not the highest. He is a local max. He's a high point, but not the highest. He's an important point for stuff we get into in the future. Local min would be a low point, but not the absolute lowest. So this guy right here, he's a low point, he's a local, min. That's terrible. So you have a local min at 1, and you have a local max. Does that make sense? Okay, again, you're gonna have to draw some pictures today, and so they're gonna say, I need a local min at 0. So you want to make a low point, like a little dip, but you don't want to make the lowest point on the graph, if that makes any sense to you. And then this right here is our absolute max. It is a cusp, and it'll come into play with things that you do in the future. All right. Now, probably the most mathy of today, which you're not even going to be doing this on tonight's homework, so don't freak out just yet. We're going to be working on this more even tomorrow. But we have to know how to find critical points. I want to teach it to you today, even though I didn't give you homework on it. There's methods to my madness. Just trust in me. Trust in me. I'm here for your math needs. Okay. Let me explain what critical points are. I'm using the definition because this is very important. I left off this definition for years until I finally realized it a few years ago, and I was like, I'm a moron. Which is why certain things didn't work out. Let's see, be an interior point in the domain of F. That is the portion that I actually left off for many, many, many years. My poor children were led astray. No, they did fine. Then C is a critical point of F if F prime of C equals 0 or F prime of C is undefined. So what we're going to be doing in the future is we're going to be finding where we have maxes and mins. And in order to do maxes and mins, you need to find these points that are called critical points. Let me turn it over just real quick. That guy right there is a critical point. That guy right there is a critical point. That guy right there, that guy right there. And notice what a critical point has to equal. Its derivative has to equal what? 0 or be undefined. But I think this was the point I actually kept messing up. C has to be the interior point of the domain. I never actually wrote the whole entire formula out. That's an actual important thing, and I'll show you in a minute with one of the examples that we do, okay? So here's what you'll be doing. Again, not for tonight's homework, but you'll be doing this as part of tomorrow night's homework. You'll be find possible critical points. That's what the directions will say. And they will give you a function. And it's really quite simple, as the definition told us to do. I take a derivative, I set it equal to 0. That's my critical point, possibly. Maybe it's not, maybe it is. We're going to find out, okay? So take a derivative for me. What's the derivative? 2x plus, set it equal to 0, solve. Is this point right here on the interior domain, meaning in the inside of this original function? Well, what's the domain of any quadratic, y'all? All reals. Is -1 inside of it? Sure. So that is here's what you would just say. It's a possible critical point. Done. I just found a possible critical point on that function. Easy. Let's do a harder one because that was just so unchallenging for you. And let's make it worthwhile.
Yeah. Right. Jensen.
Let's do this one. I would like you to find the critical point, possible ones, on this one. So I will talk you through this because I know it's been a while. You've had a whole day off. Slightly, not really. Ashlock gave you 20 papers to write, so, you know, what else? I know, I'm sorry.
It'll be an easy one, like 10, 15 minutes.
Okay, so this is really x. I'm going to write it like this, 9 minus x to the 1/2. Okay. Now, I don't need you to do u's that much anymore. If you feel like doing the u's, I'm fine with that, but I think you should be able to take this product and do a product rule without a u. So the derivative of x times 9 minus x to the 1/2 would be first times, what is the derivative of this second? How do I write it? 1/2 9 minus x to the what power? Times what chain?
-1.
Times -1. So first times derivative of the second plus second times derivative of the first, which is 1. I'm not going to write that down. You have to clean these up, unfortunately. So this is a -1, a 1/2, and an x. I'm going to call it -1/2 x. A 9 minus x to the -1/2, and a 9 minus x to the +1/2. Way back in September, I showed you how to simplify this by factoring, and you have to do that. You have to write this as one fraction. So what can I factor out of these two? 9 minus x to the what power? Lowest power. Put a big funky bracket. So if I take a 9 minus x to the -1/2 from this group, wouldn't I just be left with -1/2 x? Okay, so write that down. Plus. But if I take a 9 minus x to the -1/2 from a 9 minus x to the +1/2, what happens to it? Do you remember what happened? It becomes one of these quantities. So 9 minus x. I mean, if you want to put it in parentheses, you can. Combine your like terms. -1/2 and -1 make -3/2 x plus 9. And then what do you do with this guy? Bring him to the bottom. Like I said, this is like the hardest one you'll do, and you won't do many of these, so don't freak out. So this is your derivative. To find the critical point, you have to set it equal to 0. Well, what do you do when you set it equal to 0? Well, again, if you go back to the definition of critical point, you have to find where the derivative is 0 and where it's undefined also. It's 0 on top, it's undefined on bottom, correct? Right? So here's what you pretty much do. Just set your top and bottom equal to 0. That's really what you do to find if it's a critical point. So -3/2 x plus 9 equals 0, and then do 9 minus x to the 1/2 equals 0. So this one is good old-fashioned easy algebra. Let's see, multiply by the reciprocal. Gosh, it smells like
Yeah.
gasoline outside. Firecrackers or something. What is this, 6? And then this one, I mean, just look right here. What would x have to be to get that to be 0? 9. I mean, you could square both sides, and obviously you get 9. Now, here's the problem. One of these is a critical point. The other one actually isn't.
Like in your calculator, it should go table.
Why can't they both be? Okay, to be a critical point, you have to be on the interior of the function. And if you go back to this original function right here, just to show you, I have it already pre-graphed. Is 6 on the interior? 1, 2, 3, 4, 5, 6. Is 6 right there on the inside? We're fine with 6. Is 9 on the interior? No. 9 is right there at the end. So 9 is not actually considered a critical point. This is your only, all that for 1 point. Did you not love this? You're all like hating it. I was like, I love this stuff. You can, but you have to do this by hand. So it's
Wait, positives can't be a point. Or what is that? What does that say? I can't-
a possible critical point. Sorry.
I was like.
Sorry. Okay. So one more thing and then we're totally done. But again, what's this whole thing that you're doing? There's an idea behind all of these little bumps in the graph, okay, are all critical points that you're going to have to know how to do without a calculator. Because yes, you could look at your calculator and find out where the bump is, okay? And then there's this idea of these endpoints being absolute maximins if they give me an interval, and that's what our last theorem is about, and that's what we're gonna do right now and be done, and we'll be done with our last example. Excuse me, hold on, there it is. I'm gonna switch here. All right, and this, what, honey? John. All right, last and final thing. Talked about critical points, talked about locating absolute extrema. This is the last and final thing. And again, I'm going to give you a definition. It's going to sound complicated. It's not really that hard. I'll show you exactly what to do. Let f be a continuous function. That's an important point here, by the way, because if it's not continuous, we're going to have issues with it in the future. So over a closed interval, we'll call that interval I. Then the absolute max and the absolute min over I must occur at the endpoints, which we've talked about, at the endpoints of I or the critical points. Of f and I. And I know you're like, Miss Setta, you've been saying this already. I feel like yeah, just write it out, okay? It's important. Your absolute maxes, when they give you an interval, can only occur on the endpoints or if there's a critical point in between them. On the endpoints or if there's a critical point. I'm going to do one example, we're done. And this is literally the hardest part of the math you'll have to do tonight. There's the one I just showed you about critical points you won't even have to do. So last and final example, I'm giving you a formula for a function. Here we go. And I'm going to give you an interval, 1, 3. And I would like you to find, absolute max and mins. Okay, I do not want you to graph this. You can graph it to double check, but I want you to do this all by hand. So, locating absolute extrema theorem right here says that it's got to occur at the endpoints or at a critical point. So, here's the first thing you're going to do. Take a derivative. What's the derivative of negative x squared plus 3x minus 2? Set it equal to 0. Tell me what that critical point is. What is it? 3/2? Okay. Is 3/2 inside of this interval? Okay. So we're good because we want it to be in the domain. You are then going to make a table. This is really the easiest thing that the way that I do it. Okay. You are going to take each of these endpoints and you're going to put 1 here, 3 here, and since this guy is inside of it, I'm going to call it 1.5. You put that in the middle. And then you find out what the f of x, you go back to the original and tell me what the y is. Now, if you don't remember how to do that, you can actually just plug it into your calculator, negative x squared plus 3x plus 2. Let me turn this one off. Oops, off, and let me turn this one on. And then you can go into your table and let the table do the work for you. Oh, good, I already have it there. So when x is 1, y is 0. When x is 1.5, y is 0.25. You can plug them in, but it's just easier to do it that way. And when x is 3, I get -2. Out of those 3 numbers, which one of them is your max, your absolute max? 0.25, right? That is your absolute max. Which one of these is your absolute min? Notice your max occurred at a critical point. Your min occurred, though, at an endpoint. 1, nothing occurred. Your maxes and mins can only occur for absolute max and mins can only occur at endpoints or critical points. That's the whole idea of today. That's it. So 4.3, 91, 93, literally you're going to be given a picture. They're going to say, okay, tell me where the absolute max is. Tell me where the absolute min is. Tell me where a local max is. Tell me where a local min is. Then they're going to make you draw one. I mean, it's very easy. There's not a lot of math right now, but tomorrow there'll be fun math. Tomorrow will be fun.
On that problem before we I just like writing things right.
Oh.
The graph. How do you know which one's wrong and which one's right?
Let me stop this because I'm realizing I'm recording.